Okay, good morning everyone. Today we will going to discuss about the chapter number 1st of 10th standard NCERT real numbers. So all of you know about the real numbers can be categorized into two categories, which is rational number and irrational number. So in a rational number, we all know that if the number can be in the form of a p upon q, where the q is not equals to 0, we call them rational number. On the other hand, an irrational number, we can say that when the number is not in the form of a p upon q, where the q is equals to 0, that is irrational number. Or all those number which can be in the form of a square root, where the square root is not going to be solved, as well as the pi is considered as a irrational number. Okay, so all the sides of these numbers are called real number. Let's study this real number. Let's look here. Okay, so in a real number category, first we will know about what are the real numbers, what is natural numbers, integers, and all that. Now Euclid is a mathematician who discovered that Euclid division lemma and algorithm. By this Euclid division lemma or algorithm, we can find that the particular integers exist or possess in between the two positive integers. The two positive integers, let's take the a and b. So if these a and b are the two positive integers, then we can say that q and r are the number which is exist in between a and b, as well as they possessed in between the number or a and b. Right, so Euclid says that given two positive integer a and b, there exist unique integer. Now these numbers are the unique integer. Look at this, may I highlight it? These are the unique integers, right? So that means it can be q and r. Not other than that. It will be fixed for any two positive integers. If they are a and b, then the unique positive exist numbers are q and r. In this way, that it satisfies the equation a is equals to, here should be a is equals to bq plus r. Okay, as we studied, this a and b are the two positive integer. It can be anything, and q and r are the two positive unique integer which exist in number a and b. Okay, and here is the important thing, that r would not be greater than 0, as well as it can be equals to 0, and it would be less than b. Look at this. Here r, which can be represented here, look at this, it is a is equals to bq plus r. So we can say that this a is the dividend, b is the divisor, where the q is the quotient and r is the remainder. So if we divide the a by b, then it will be q and r, which are the quotient and remainder. All right. Now if the q and r are the remainder, so it will satisfy this equation as a is equals to bq plus r. And most importantly, the r value can be 0. If the division is completely get over, we call it terminating decimal expansion. So if the 0 comes in the end, that means the remainder will be 0. So r can be 0 and r can be more than 0 as well. Sometime we can see that the remainder will not getting 0. So we call them, yes, it's non-terminating. Then but it always be less than b. So b is our divisor, remainder is always less than b. It cannot be equals to the divisor. Okay, let's go to the next slide, or there is an example as well. Look at this. For an example, if we are taking this as a is equals to bq plus r, if a number is 13, which is a dividend, the b number is 2, that means these are the two integers a and b, 13 and 2. So if we divide 13 by 2, it will be completely divisible. And how many times it will be divisible? 6 times, as we can show. 2 6 are 12, If it is not 12, then it will be remain some remainder. If it is 12, then 2 6 are 12 plus remainder will be nothing, so we will write it 0. But if the A dividend is 13, then here will be the remainder, which is 1. 2 6 are 12 plus 1 is left. That means here in this condition, if A is equals to 13, B is equals to 6, then Q will be 6 here and the remainder will be 1. Okay, so it is satisfying this equation that A is equals to BQ plus R, where the R value can be 0 and greater than 0 but less than B. So 13 is equals to 2 into 6 plus 1. So this is called the Euclid division algorithm. So algorithm is basically the set of the mathematical calculation, and Euclid apply purposely to finding the HCF of these cases by applying the Euclid division algorithm. Okay, is it clear? So if the question comes in exam that what is Euclid division algorithm in 1 mark, so you have to write that if we are taking the two positive integer A and B, then they exist unique integer Q and R, which satisfying the equation A is equals to BQ plus R, where R is equals to or less than greater than 0 but less than B anytime, every time. Okay, let's go for the second slide. Okay, so in Euclid division algorithm, we studied that to obtain the HCF. Here it is. Why we are using this Euclid division algorithm? For finding the HCF, highest common factor. HCF of the two positive integers is A and B, with A is greater than B. Following these steps, so apply the Euclid division algorithm to A and B. So we find whole number Q and R such that they satisfying the equation A is equals to BQ plus R, where the R is equals to and greater than 0 but less than B. So we studied this, that how we will apply the Euclid division algorithm in a particular question where the two numbers are given A and B. Alright. Okay, so now we will take some examples of regarding of this to find the HCF of the two following numbers. Look at this. If R is equals to 0, if your remainder comes 0, that means A will come only the form of BQ, A is equals to BQ. So if R is equals to 0, then D is the HCF. What is the D here? D is your last divisor, which we get it from which we get it the remainder 0. So D is the HCF of A and B. If R is not equals to 0, apply the division algorithm to B and R. Now what is B and R? B is the same number by which we are dividing, that means it is the divisor here, and the R is the remainder of our next step. Clear? So we will continue. If our remainder will not come 0, we will continue this process for getting 0. Okay, this case when the remainder becomes 0 or when the remainder is not become 0, continue the process till the remainder is 0. So you have to repeat this process by finding A divided by B, then whatever it comes in the remainder, then again you can divide this remainder R by the B, then again if the remainder will not come 0, then again you can proceed this procedure. So continue the process till the remainder is 0. So whenever you get the remainder 0, those particular B value, that means the divisor which you get it 0, that remainder divisor will be your HCF. So the divisor at this stage will be required HCF. So when you will get the remainder 0, that divisor is your HCF. Alright. Okay, so this Euclid division algorithm is very important. The question may comes that find the HCF in between the two following digits which is given. Look at this, how the question will come. Okay, so here it is using Euclid division algorithm to find the HCF of 12,576 and 4,052. So how we will start the questions, like if this is our A and this is our B, because your greater number is always A, so we can say since because we know that this 12,576 is greater than 4,052, so we apply the division lemma to find the HCF, correct? So as we know that we will follow the Euclid division algorithm, which is A is equals to BQ plus R. So you have to follow this equation, A is equals to BQ plus R, where the A value is the greater one and the B value will be the short one. So this is our number A 12,576, which is equals to B, which is 4,052. Now if you divide this number A by B, you will get it some remainder, because it is not completely divisible. This is not completely divisible. So if you divide it, it may be, look at this, this is exactly more than 4 times. So that means 4 4s are 16, sorry, it can be exactly more than 3 times. So if we multiply this number 3 times, it will come somewhere around, let's do it, 12,156. Now that means 420 will be left, which can be the remainder, right? So this B 4,052 multiplied by the quotient, which is 3, then plus the remainder, which is 420. All right, we will just simply divide it like this: 12,576 divided by 4,052. So you will get it the quotient 3 times, which is 12156, and exactly you will get it 420 as a remainder. So how we will write in the division algorithm? This is your A, which is equals to B into Q plus remainder. So as we can see here, it is exactly look like this: A is equals to B into the Q, which is 3 plus the remainder 420. All right, now we have to write the statement here. What was that? It states that since the remainder is not equals to 0, so if the remainder is not get 0, we will proceed this procedure again. So we apply the division lemma for now, this time with this B value and the remainder 420. So 4,052 and 420 to get the next step. So this is our step number 1. Now we will do it in a next step by taking this B and R as follows. So here our B number will be 4,052 and the remainder is 420. So this B will become A and this remainder will become Q in the next step. So A is equals to B into Q. Now how many times this 420 will be divisible? 4,052 will be divisible by 420, exactly more than 9 times. So as you can divide it, it will be multiplied by 9 and some remainder will be left. So what remainder will be left in that case? 272. Okay, again in that case also the remainder is not getting 0, so again you have to write the statement: we considered the new divisor 420 and the new remainder 272, apply the division lemma to get it the next number, because here also we are not getting this 272, remainder is not getting 0 because as it is 272. So that means we have to repeat this procedure again. So in step number 3rd, you will take these number now 420 and 272. So this 420 will become A and 272 will become B value. Now as we can see in this value 420 and 272, it will be divisible by only 1 times. That means the remainder again will be left in that case, which is 148. Now we can proceed this procedure again. Now we continue this procedure till the remainder will not get 0. So as we divided this 272 by 148, again it will be divisible by 1 time and again the remainder will be obtained. which is 124. So we will proceed it again, 142 as the A and the remainder will be as a B. Again it will be divisible by 1 time and again the remainder will be 24. So next time again we will take this A and B, we continue this procedure, it will be 5 times, the remainder will be 4. Then at this stage, when we are taking this B value which is 24 and the remainder which is 4, it is exactly divisible by 6 times, 4 6 are 24. So now at this stage we will get to know that the remainder will become 0. So at this stage we will get the remainder 0. That means we can say that this 4, because it was the remainder in the previous case, by this it is the divisor in the last stage, so the last stage divisor will be our HCF. So as we can see, the remainder has now become 0, so our procedure stops. Here we stop says, then since the divisor of that last step at this stage is 4, so the HCF of these two number is this 4. Okay, although in an exam that this much big question will not come, they will give you the sufficient number in which you will get the answer within 3 steps or 4 steps. Okay, so now we all studied the Euclid division lemma to find out the HCF between the two numbers. Now we will take the fundamental theorem of this arithmetic. Look at this. Fundamental theory of arithmetic. What it is? This says that every composite number, we all know about the prime number and the composite number. Prime numbers are those numbers which can be divisible by 2 or the multiple of 2, and the composite number which can be having more than 1 or 2 as a common factor, like more than 2. So every composite number can be expressed as the product of prime, and this factorization is unique apart from the order in which they occurs. So that means if we are taking the factors of any large number, the factors of this particular number, because it is a composite number, so the factors are not comes only in the form of 2, it may be any other or more than 2. So look at this, last digit is 0, so we can divide it by 2 continuously 3 times. Then whatever it is, simply division, you can just divide this number 32760 by 2, you will get it the half of this number, which is 16,380. So last number is again even number, so we know that if the last number is even number, we can further divide it by 2 only, so it is again divisible and again it comes half of the number. So now it is again 0, we will again divide it. Now the last number is not the multiple of 2 or not an even number, so that means the 2 will not divisible in that case. So that means if the last number is 5, so now we will check it that the number is exactly divisible by 3, and so you have to know about what is the divisibility test of these number. Divisibility test of 2, 3, 5. So the divisibility test of 3, by checking it, you have to do the sum of all these digits. If it is the multiple of 3, then only it will be divisible by 3. So as we can add these number, 5 plus 4 is also 9, 9 plus 9 is 18. Now 18 comes in the 3 tables of, or it is completely divisible by 3, so that means it will be divisible by 3 here. Again it comes 1365. Now again the sum will be divisible by 3, so we will again further divide it by 3. Now it comes 455. Now we know that 455, let me raise it. Now we know that if we further divide this number by 3, it will come 455. Now 455, the sum of these digits will be 14, and 14 will be not divisible by 3. So now we will divide it any other digit than 3, but we have to take the prime number here, right? So we will not take it the 4 because it is already 2 by 2, so it is not divisible by 4 as well, right? So we have to take only prime numbers, 2, 3, then after 3 it will be 5. So by 5, it 455 will be completely divisible by 91 times. Now after that we will divide this it becomes 91. And again, because if the last number is 0 and 5, that will be the divisible, that can be divisible by 5. Okay, now here it comes 91, the last digit is 1, which is not divisible by 5. Now we will take it other digit, so after 5 the prime number will be 7. So as we will divide this 91 by 7, it will be divisible by 7 13 times. Now 13 is the prime number, that means it will be divisible by 13 only. 13 ones are 13, that means here our factorization will be completed. So what are the factors of this number 32,760? 2 by 2 by 2, 2 raised to the power 3. So we will write this situation as in this form. Look at this. 32760 can be written in the form of a 2 1 2 3. 2 raised to the power 3, then 3 comes 2 times, so we will write it 3 square, then 5 comes 1 times, then 7 comes 1 time, and then 12 13. So these are the factors of 32,760. Okay, it's clear. Now so if the question comes find the factors of 32760, so you will find it by this method. All right, our next slide is visiting the irrational number. As you know that irrational number are those number which cannot be represented in the form of a p upon q, right, as well as those number whose are in square root, and the square root is not going to be solved in that particular situation. So let's p be a prime number. If p divides a square, then p divide a also. Now this is a theory, remember this theory. P be a prime number if there is a prime number p, and if p divides a square, and this p is the prime number which can be divided a square. A square can be any number. So if p divides a square, that means p can also divide it by without a square, as it can be divided by a. For an example, if you are taking it, 2 is divisible by 24, or we can take it here, 2 can be divisible by 24 square. That means 2 can be divisible by 24 also. Okay, so in that case, if p is a prime number and it can be divisible by a square, that means it can be divided without square as well. So in this particular theorem, we will prove that if any number is irrational or not. Just like this theorem, under root 2 is irrational. How we can prove it that this under root 2 or under root 3 or under root 5 can be irrational number? Okay, sorry. All right, so if we have to prove that any irrational number, that how we will represent it, any irrational number is irrational number. So in that case you have to prove it. Let's suppose that it is not a irrational number, let's suppose that it is a rational number. So if we think that under root 2 is a rational number, where if any number is a rational number, it can be written in the form of a p upon q, or instead of p upon q you can take any other number like a upon b. So where these a and b are co-prime, let's take it these are the co-prime, and the co-prime are those number which have the no common factor other than 1. So if these numbers are co-prime, look, these a and b are co-prime. So if a and b are co-prime, so that means we cannot further divide it. So under root 2 can be represented in the form of a upon b, and because it is a rational number, so we can say that b will not equals to 0, correct, and a and b are co-prime, so we cannot cancel it further. Now if we are solving this square root by the rationalization, so we have to make the squaring on both sides, because it is in square root. If we are doing the squaring on both sides, then square root of 2 will be 2. Here it is, square root of 2 square root of any number can be simplified, which is square can be cancelled by the square root, or you can say if it is under root 2 into under root 2, then under root 2 can be simplified. Okay, so 2 square, square root of 2 square is 2, and on the right side, because we have doing the squaring on both sides, so this a upon b also comes in the square form, which can be written as a square upon b square, right? So now we can do the transposing, or here b square is equals to a square upon 2. Is it right? B square is equals to a square upon 2. Now by this case we can say that a square is divisible by 2, because as we can see there is a division sign, the fraction means division. So a square is divisible by 2, so that only it will come b square, right? So we check it that a square is divisible by 2, so we will get it b square in that condition. So as we can see by the theorem only, if it is divisible by a square, that means it can be divided a also. So here also we can say the same thing. Here 2 divides a square, so it can be divided a as well. So we can say that here the a value has 2 as a multiple, and let's write it another constant. So we will write it, ab is already there, so I will write it here c. So a square is equals to 2c. Why? Because a is divisible by 2, that means a is in the form of the multiple of 2, because it is divisible by 2. So that's why we will write here that a has the prime number, because it is divisible by the 2. That's why we will return here a is equals to 2c, where c is some integer. Is this clear? All right. Now after that we studied that how it comes b square is equals to a square upon 2. Now by the same procedure, if we transpose the b square from here, or we get it the b value, which is 2c, right? So if we substitute the value of a as 2c, then there should be a square. So if that was a square, we studied that previously it was a square, it was like 2b square is equals to a square, where we have seen that the a value will be 2c. Now if we are putting or substituting the value of a here 2c, so 2c square will be 4c square, correct? Therefore we will get it 2 will cancel by 4 2 times, so b square is equals to 2c square. Now from here as well, if we transpose it this 2 down, it will be c square, which is equals to b square by 2. Now if it is b square by 2, that also means it will be divisible, and you will get it the c square in that condition. So that means b square is also having the 2 as the multiple, because it is completely divisible by b square, and it will get it c, right? So we will say that the b square here 2 divides b square, that means it also divides b by the theorem which we studied, that if 2 divides b square, that means it can be divided b as well. So that means we can say that the b is also having the prime number of 2, as well as in a is also having the prime number of 2. That means actually this a and the b both are having a common multiple. But in the first case where we studied that, we suppose a and b are the two co-prime number where they have no common factor other than 1. It's proved wrong, because in a and b both having the 2 as the multiple, so we can say that our contradiction was wrong. We supposed it that it will be the rational number, as a and b are the co-prime, but we seen here that a is also having the 2 as a common factor, as well as b is also having the 2 as a common factor, because it is completely divisible. So we can say that this create a contradiction, that a and b are no common factor other than 1. Why it is having? Because we suppose it that these are the co-prime number. That co-prime number means they have no common factor other than 1. That means it is completely false. So we contradict has arisen, this contradiction has arisen because of our wrong assumption. So that means we assuming it wrong, because it is a rational number which is actually not a rational number. So if it anything is not a rational number, its directly irrational number. So that's what we proved it here, that if a number is not a rational number, it will be irrational number. So we conclude that under root 2 is an irrational number. Alright, we have to prove it that under root 2 as irrational number. So we think it differently, that under root 2 is a rational number. So if we able to prove it wrong, that means we assuming it wrong, that means this contradiction has come arisen because of our wrong assumption. So that means it will be not a rational number, so it means it is irrational. Correct? So the answer will come here, that under root 2 as irrational number. Okay, now next slide is rational number and their decimal expansion. You all know about the decimal expansion. If any number which is a rational number, just like 2 upon 3 or 1 upon 7 or anything, if we able to divide it and the remainder will get over, that means if you get it the remainder 0, that means it is a terminating decimal expansion. But if the remainder is not coming 0, that means we are dividing it after decimal so many times and the remainder is not coming 0, that means it is the particular number which is non-terminating. Now this non-terminating numbers is also classified into two categories, whether it is non-terminating repeating or non-repeating. If a particular digit is continuously repeating, just like if you divided any number by 3, 10 divided by 3, so one remainder is coming continuously, so you have to put it decimal and 0, then the question will be 3 3 3 3 every time. So if any number is coming continuously, we call it repeating or recurring. So that particular decimal expansion will be non-terminating but repeating. And if the number is not repeating, for an example, if you are dividing any number and it will become 3.12476 and no number is repeating and the remainder is just on and on and on, so this kind of a number is non-terminating and non-repeating or non-recurring. Okay, so in this slide we will study about that. Let x be a rational number whose decimal expansion terminates. All of you know the meaning of terminate, that means end. So if our division is end, that means the remainder will become 0, then x can be expressed in the form of p upon q, because it is terminating decimal expansion, so we will write it, the denominator will become 0. If it is terminating, that means the remainder becomes 0, yes, obviously. So in that case a is equals to bq plus remainder will be 0. So in that particular case your number p upon q, your number is a rational number perfectly, because all the terminating decimal expansion are rational number, where the p and the q are co-prime. Now it cannot be further divided because these are co-prime, and the prime factorization of the q is in the form of a 2 raised to the power m and 5 raised to the power n. It can be anything, so we can mark it the power differently. So 2 raised to the power m and 5 raised to the power n. Okay, so we studied that if any number is a terminating, so it can be represented in the form of p upon q, where the p and q are co-prime, as well as the prime factorization of the denominator in the form of 2 raised to the power m and 5 raised to the power m, because this is just shows that all the terminating decimal expansion has the denominator in the form of a 2 raised to the power m and 5 raised to the power n, where n and m are non-negative integer. Look at this, such an example, 3 upon 8. So when we are doing, we can just check the denominator and directly said that the particular number is terminating or non-terminating by making the factorization of this denominator. Just like if it is in the form of a 2 raised to the power and a 5 raised to the power, so it will be terminating. So if we are making the factor of 8, it can be 2 into 2 into 2, because there is 2 has a factor which can be in the form of a 2 raised to the power m and 5 raised to the power n, right? So it means it is terminating. If there is any one of them, that then also it is terminating decimal. If whether it is 2 or 5, both cases are terminating. But other than 2 and 4, if there are any other factor other than 2 and 5, then it will be non-terminating. So let's take the another example, 13 upon 125. When we are doing the prime factor of 125, it will be 5 cube. As we can see, it is also in the form of a 2 raised to the power m and 5 raised to the power 1, where the 2 raised to the power m we can consider it is 2 raised to power 0. So in that case also it is in the form of a 2 raised to the power m and 5 raised to the power m. So that means it is also a terminating decimal expansion. Is it clear? Okay, so this is all from my side. We studied today that what are the real numbers, how we differentiate all the real numbers into the different categories like a rational number and irrational number. Then we studied the Euclid division algorithm and what is the use of it. Then we will find the SCF of that, then arithmetic progression of any particular number by taking the prime factorization. Then we studied about how to prove an irrational number is actually an irrational number by proving it or assuming it rational number, right? And the last but not the least, we have seen that how the terminating decimal expansion and the non-terminating decimal expansion can be classified by just taking the denominator or making the factors of it. Okay, hope you like it. Thank you.